Which polymer has hydrogen bonding between its chain? Well, I know it's definitely not polyethene. That's just ethenes that have had the double bond broken and formed long chains of single bonds, and PVC, polyvinyl chloride, isn't either. They're addition polymers. Terylene is a polyester. Kevlar is a polyamide with a peptide link in it. So my answer is A. Let's have a look at those then. So this is Kevlar with benzene rings separated by polyamide links, C double bond O NHs, C double bond O NHs, and so I've got N to H here. I'm going to have hydrogen bonds between the chains. This is polyethene, where the C to C has had a double bond and it's broken, and I've got an addition polymer. PVC is very similar, except one of the H's is replaced by a Cl before you polymerize it, so I've got CH2CH Cl with a double bond as a monomer. And terylene is a polyester, so I've got dipole-dipole attractions, but I haven't got any hydrogens bonded to oxygen. So my answer is Kevlar A. I can also remember that because Kevlar is very strong, used to make bulletproof vests and motorcycle helmets, and hydrogen bonding will help strengthen the bonding between that structure, between those chains. Which structure shows part of a peptide link in a protein? Well, a peptide link is a C double bond ONH, a bit like this being a peptide link here in Kevlar. I've got two of those, funnily enough. Both of these, there's a CONH, CO, and a CONH, but you never get two COs separated by an NH in a protein, not when amino acids join together. So my answer is D, a simple peptide link. Two strands of DNA are joined together by hydrogen bonds. Which is correct? Well, I've referred to my data book, and on every O and every single N I put a lone pair of electrons, and then I bond those in hydrogen bonds going round in rainbows between the bases. Then the lone pair of electrons on the oxygen bonds to the delta plus on the H, because remember this is a polar bond here between the NH2s, so make all the NH2s polar bonds. Delta plus is on the H's of the NHs, the delta plus bonds to the lone pair of electrons on O's and single N's. Here I've got an NH with a delta plus on the H going round and bonding to a lone pair of electrons on the N. Lone pair of electrons on the O will bond to the delta plus on the H there. So I've got three bonds between guanine and cytosine. NH2, delta plus on the H of the NH2 on that polar bond will hydrogen bond then to the lone pair of electrons on the O. And I've got an NH here, I've got a delta plus on the H, will hydrogen bond round to the N with the lone pair of electrons. So let's have a look. Adenine and guanine form two hydrogen bonds. Adenine and guanine, no adenine bonds to thymines. That's incorrect. Cytosine and thymine. Cytosine bonds to guanine, not thymine, so that's incorrect. Guanine bonds to cytosine. Guanine does indeed bond to cytosine, and I do get three hydrogen bonds. That's correct. Let's just check the last one. Adenine and thymine. Adenine and thymine do indeed bond together. They're complementary bases, but they only form two hydrogen bonds, not three. So my answer is C. Which is not responsible for the conduction of electricity. So conduction of electricity is where you get electrons on the move, called delocalized electrons. Sodium ions, well, ions are plus charges, so sodium ions are Na plus charges. In molten means it's liquid. These ions can move, these plus charges can move, so that would conduct electricity. Electrons between the layers of carbon atoms in graphite, they're delocalized between the layers in graphite. Bonding electrons in a metal, yes, the electrons get delocalized around in a metal, and it conducts electricity. You probably know that graphite and metals conduct electricity anyway, so B and C are fairly obvious to be true. Lone pairs of electrons on water molecules, no, they're bonded to the oxygen. They're not delocalized, so my answer is D.